Welcome to the second video in this three-part Excel training for engineers. In this video, we're going to look at how to handle complex calculations in Excel with ease. Thanks again for watching the first video and giving me your questions and feedback. In that video, I showed you how to use named ranges in calculations instead of cell references to make formulas less confusing and more readable. I also showed you how you can convert units right in Excel using the convert function without having to look up conversion factors from other sources. And if you didn't get a chance to watch that video, go back and check it out right now before you watch the rest of this one. In this video, I'm going to show you how to do something in Excel that only a small percentage of engineers know how to do. So let's get into it. Okay, with all these preliminary calculations out of the way, the next thing we need to do is calculate the required total area for the bolts. And to do that, we need to solve this system of nonlinear equations. Now there's 5 equations and 5 unknowns here. And the reason I say that it's a system of nonlinear equations is really just because the first 2 equations are nonlinear. And that's because that area is in the denominator on the right-hand side of the equation. The remaining 3 equations are linear equations, but because those first 2 are nonlinear, that makes this whole system nonlinear, and we can't just solve it using traditional linear algebra methods. So like I said, that area is showing up in the first 2 equations in this system of equations, and to solve that system of equations for area, we're going to use a tool that's built into Excel called GoalSeek. Now GoalSeek can be found if you go up to the Data tab, and then in the Forecast selection, open the What If Analysis drop-down and select GoalSeek. GoalSeek has 3 inputs. The first one is the set cell. That's the value that you want to change to a certain value, which you specify then in toValue. And then the last entry is the by changing cell, and this is the cell that you're going to modify in order to get the end result that you want in the set cell. Now I've kind of flowcharted here how we're going to use GoalSeek to solve this system of equations. The first thing we're going to do is we're going to take a guess at the total area of the bolts that's holding the lid on the pressure vessel. We're going to use that guess then to calculate sigma max and sigma min, the max and min stresses in the bolts. From there, we can calculate the mean and alternating stress in the bolts. And once we've done the mean and alternating stress, we can calculate the equivalent stress. Then we're going to do a check to see if the equivalent stress is equal to the endurance strength divided by the safety factor. If those 2 quantities are not equal, then we're going to use GoalSeek to go back and keep guessing at the area until they ultimately are equal, and at which point we'll have the area value that we're looking for, and we can end the GoalSeek routine. Now all this happens automatically within Excel without us having to do all these iterations. The software just does it for us. And if it's not clear exactly how this works, just bear with me. As we go through this example, you're going to see exactly how it's done. Okay, so back in our spreadsheet again, the first thing we need to do is enter a space where we can put the guess value for the area. And this is going to be the total area. So I'll go ahead and copy this formatting down, and we're actually going to need to create 6 more entries here. We're going to create a guess value for the area, and then we're going to enter our 5 equations. So I'll just go ahead and enter or create 6 new rows here in our table of calculations. The first one, again, like I said, is total bolt area. And this is just going to be a guess for now, so we'll just enter a value of 5 square inches. We'll call this A underscore total. The next line we need to enter in is the calculation for the maximum stress. And in fact, while I'm at it, I'm just going to go ahead and enter all these descriptions in. So we'll do minimum stress, as well as mean stress, alternating stress, and the volt equivalent stress. Okay, and I'll also create the named ranges for those. I did total area already. So we'll do sigma underscore max. We'll do sigma underscore min, sigma underscore mean, sigma underscore alt, and finally sigma underscore EQ underscore 2 to distinguish it from the bolt equivalent stress that we calculated in this row already. Okay, now let's go ahead and enter in that calculation for the maximum stress. As I showed you before, the calculation is going to be 1.5 times the max force. That's because we're going to assume that the preload is equal to 150% of the max force plus the component of the alternating force that's carried by the bolts. And we decided we were just going to assume that that was 2% of the max force. Okay, and then that's all divided by the total area to calculate the stress. Next, we can go ahead and calculate the minimum stress. That equation is very similar. It's going to be 1.5 times F max plus 0.02 for 2% times the minimum force. Again, divided by the total area. Now the mean stress is then calculated as sigma underscore max plus sigma underscore min divided by 2. The alternating stress is where we include the stress concentration factor. So that's going to equal K underscore thread divided by 2 times sigma max minus sigma min. And then finally, the bolt equivalent stress is going to equal sigma underscore alt for the alternating stress plus the endurance strength, SE, divided by the ultimate strength times the mean stress, sigma underscore mean. Okay, and that gives us our bolt equivalent stress. And we'll put some units on these, PSI for all. So now what we need to do is we need to find the value of the total bolt area that's going to set this bolt equivalent stress calculated here equal to this bolt equivalent stress we've calculated using these other equations. But GoalSeek can't tell when two cells are equal to one another, so what we need to do is actually subtract the two values and set a goal of obtaining a value of 0. So we'll just create a row here called equivalent stress difference. And the calculation there will be sigma underscore EQ underscore 2 minus sigma underscore EQ, and the units on that will be PSI. Now, of course, we have a difference here. This value is not equal to 0, and that's because our total bolt area has not been chosen appropriately to make the equations work out. Now, we could probably guess at it, and we could eventually get there, but we could also use GoalSeek as well. So before we do that, I'm going to increase the number of decimals here so that we can see how the value is actually changing. And we'll go ahead to our Data tab, select What If Analysis, and then GoalSeek. Okay, we want to set the cell right here, this equivalent stress difference that we calculated, to a value of 0. And we want to do that by changing our guess value for the total bolt area. Okay, and that's all there's to it. We just have to enter those 3 things into those boxes in the GoalSeek window, and then we just click OK. And GoalSeek iterates until it gets this equivalent stress difference equal to 0 within some tolerance. And we find that the total bolt area required for this design to meet the design requirements of infinite life with a safety factor of 3 is 4.46 inches. Now we don't need to have all those zeros on there, so we'll just reduce it down to 3. Change the fill so it matches everything else. So the next thing we can do is take the total bolt area, divide it by the number of bolts to figure out the area per bolt that's required so that we can actually size the individual fasteners. So we'll just call this area per bolt. And this is going to equal A underscore total divided by N underscore bolts. And of course that is in units of inches squared. Well, as you know, bolts are not specified by their area. They're specified by a nominal diameter. So we need to take this area that we've calculated and determine what the nominal diameter is of the bolt that we're going to need to specify for this design. So I'll go ahead and create the third section of this spreadsheet. We'll call it results, or just result, because there's really only one value that we're concerned about. We'll call this nominal diameter. All right, we'll scoot over here so we got a little bit more space to work with. We'll expand this. The value that we're going to return is in inches. So what we really need to do here is we need to find a bolt diameter with a tensile stress area that exceeds the calculated requirement. The bolt size is not going to be correct unless it gives us an area that is greater than the area per bolt we've calculated in this cell. Now there's no mathematical relationship between the tensile stress area and the nominal diameter. We get that from looking in tables of data. So what I've already done is I've already pulled some bolt data into this third sheet in this workbook. It contains several different columns. The 2 columns that we're interested in specifically are the nominal major diameter and the tensile stress area. And I've already gone ahead and created some named ranges for those columns that contain the diameter values and the tensile stress areas. And we're going to use that in a lookup function to determine the proper bolt diameter for this design. Now you might be familiar with a VLOOKUP function, but in this case we can't use a VLOOKUP because in order to use a VLOOKUP, the value that you're looking for has to be in the far left column of the table. But in this case, the data for diameter is in the second column, and that's the value that we want to return from that column. And the array that we're going to look through to try to find the lookup value is actually in this fourth column right here in the tensile stress area. So rather than using a VLOOKUP function, we're going to do a more of an advanced lookup using index and match functions. And in order to do that, I've already set this column up to be in descending order. So the largest tensile stress area is on top and the areas decrease as we go down the column here. So let's go back to our spreadsheet and set up that calculation. The first function that we're going to use in this calculation is the index function. An index, as it says here in the description, returns a value or reference of the cell at the intersection of a particular row and column in a given range. Okay, so what does all that mean? What it means is that we are going to input an array and we're going to specify the row number in that array from which we want to pull a value. Okay, so it looks like this. We want to return a diameter. So the array that we're going to look in is diameter that we already specified in that table of bolt data on the other sheet. Now to get the row number, we're going to use another function called match. And for this, we need to specify the lookup value that we're looking for, which is this area right here. The lookup array, which is that array of tensile stress areas. And the final argument that we need to enter is the match type. We can choose 1 for less than, which means it's going to find the largest value that is less than or equal to the lookup value. 0 for exact match, which isn't going to work for us because the area that we calculate isn't necessarily going to correspond to a nominal diameter. Or we can use an argument of -1, which is going to find the smallest value that is greater than or equal to lookup value. So what this is going to actually do is it's going to look in the array for this area that we've calculated here in cell G19, and it is going to find the next largest area, find the position in the array of that next largest area, return that value into the index function, and give us the matching diameter. So I'll add the 2 parentheses here and hit enter, increase the number of decimals, and we get a nominal diameter of 1.25 inches. Make some of these columns a little narrower so we can see everything on one screen. Now that's a really large bolt size, and of course that's happening because of the number of fasteners that we've chosen. But we can look at where that value comes from. If we do this manually, we can look at the area per bolt, go here to our bolt data tab, look for the smallest value of tensile stress area that's greater than that 0.74 that was calculated, and that just happens to be this value right here, 1.073. The diameter that corresponds to that is 1.25. And we see that's exactly what's been returned to our spreadsheet in our results section. So that's how you can use GoalSeek to solve systems of equations in Excel and index and match to do advanced lookups from tables of data. In the final video, I'll show you how to use automation in Excel to avoid potential errors and mistakes in a spreadsheet like this. But before you go, leave a comment below with any questions and let me know how you're going to start using the techniques from this video in your own spreadsheets. Thanks again for watching, and I'll talk to you later.